So of course, if trig substitution works, it's going to have to work for definite integrals as well. But definite integrals will add an extra layer of complexity because we'll have to deal with the numbers that are associated. All right, so once more to the breach. When we look at our particular integral, we can see that it has an x squared minus 1 in there. So if I look at my types, it's going to be this one again, x squared minus 1. Our favorite, the secant of theta, is x over a. Okay, so you'll notice that a squared is 1. So actually, let me put that down here. A squared is 1, so a is 1. All right, and then we'll be using our trig sub, from which everything will fall, which is that the secant of theta is x over 1, right? Because a is 1 for us. Or if you like, the cosine of theta is 1 over x. That is our trig sub. And as per usual, we know we're going to need about half the page taken up by all the work we're going to have to do for the substitution, right? So about half the page becomes all the substitution work, and then the other half becomes all the integration work. Okay, so let's build a triangle. Put our angle theta. We know that cosine is adjacent over hypotenuse, or secant is hypotenuse over adjacent. So this is x and this is 1. That would make this third side, which I'll call b. B squared would be equal to, b squared plus 1, sorry. Plus 1 squared would be equal to x squared. So b squared is equal to x squared minus 1. So b is equal to the square root of x squared minus 1. Again, you can memorize that if you want, because it's in the trig substitution memorization page, but you don't really have to. You can always develop it with a Pythagorean theorem, which we do. Okay, so then let's think, what else do we need? We almost always need x. So x would be the secant of theta, right? Because if secant of theta is x over 1, then x is the secant of theta. Dx is the derivative of that, which is secant theta tangent theta d theta. And then theta would be equal to the arc secant of x over 1, or that would be the arc cosine of 1 over x. And if we need any more, we'll come back. So we'll be back for that. Let's just use that piece. Okay, so breaching over the work to get to the integral part. So I'm going to need an integral. All right, I can already tell I'm going to need something else, but let's hold off on that. So I'm going to need some numbers here. I'll be back for those. But I do know that I have the square root of x squared minus 1 over x. So that's a lot going on there. So I do notice, just by looking at this, that the square root of x squared minus 1 over x is the opposite over the hypotenuse. Can you see it? So then we'll make a note. If we look at our triangle, the sine of theta is the opposite over hypotenuse, which is the square root of x squared minus 1 over x. So we can just use that. I mean, I grant you, if you wanted to use the secant squared theta minus 1, it'll work. You'll get the same place, but it'd just be so much more work than just plugging in sine of theta. But let's suppose you don't see it. Let's suppose you're not, you don't envision that this is possible, that you can just put in sine theta. So just keep this in mind, because I'm going to go show all of this. All right, so this is the square root of x squared. X is secant theta, so secant theta squared, so secant squared theta, minus 1 over x, which is secant theta. And then dx is secant theta tangent theta. So that's secant theta tangent theta d theta. Right here, I'm using that substitution. Right here, I'm using my second substitution, right? So this is dx and this is x. And if I look at my substitutions, that's the single star, there's the double star that I keep using, those two. But again, you could have avoided all of this with this one. I'll show you. It'll show up. Just give me time. All right, now there is one other issue that I need to address, which is the numbers. Right? I don't actually want x anymore, right? I can't put the square root of 2 and 2 in here because the square root of 2 and 2 are x values. I don't have x values. I have theta values. So I need theta. So let's figure this out. When x is equal to the square root of 2, theta is the arc cosine of 1 over the square root of 2. That should be screaming out to you. Think about your unit circle. What angle has a cosine that is 1 over the square root of 2? It's pi over 4, right? So this is pi over 4. So my bottom number on my integral is going to turn into pi over 4, right here. Now my top number would be when x equals 2. So I'm going to need another one for that. So when x is equal to 2, theta is the arc cosine. You could also do arcsecant, but we don't memorize arcsecants. We memorize cosines when we learn the unit circle. So that'd be a half, and that would be this angle right here, because pi over 3 is a half and then square root of 3 over 2. So this would be pi over 3. All right, so then that gets me this number right up here, pi over 3. And I will never go back. I will never go back to the square root of 2 and 2. I'm done, right? Once I've turned this problem into theta, I never actually would need to return and back substitute in what x was. Not in this particular problem. All right, so now let's do some work. So secant squared theta minus 1. Let's see, this is pi over 4 here, and then pi over 3 right here. Secant squared theta is the square root of tangent squared theta, because that's the Pythagorean identity. And then the secant thetas will actually cancel, right? So that's nice. So let me do that. So these are gone, and that just leaves me an extra tangent theta, d theta. I don't even need my fraction bar anymore because there isn't any one. And actually, if I do it this way, then the sine of theta actually will never show up because I'll never get there. I've actually skipped and bypassed over all of that, which is fine. Right? But if you wanted to use the sine of theta, you could. All right, so then it's from pi over 4 to pi over 3. And the square root of tangent squared is tangent. So it's tangent and then another tangent. So that's tangent squared, d theta. Well, we have a reduction formula for that. We have our lovely reduction formula for tangent, which is right here, right? And I realize, by the way, that these are misnumbered, so I'm going to have to renumber these in future. So this should be 5 and that should be 6, but that's all right. All right, so tangent to the n power right there. So let's use it. So I'll just mention reduction formula. And it was number 3, right? Okay, so that would be, let me bring it back. N is 2 for me, so I'll make it tangent to the 1 of x over 1, which is tangent of x, minus the integral of tangent to the 0 of x, which is 1. So it's going to be the integral from pi over 4. Actually, there's no more integral. Take it back. Read it. It's tangent of x, or of theta, sorry, tangent of theta. It'll be that from pi over 4 to pi over 3. If we have to keep those definite integral numbers in there, minus the integral of tangent to the 0. Tangent to the 0 would be 1. So it's just 1 d theta. And again, that one is from pi over 4 to pi over 3. So then that would mean that it's tangent of theta minus theta. And then all of it is from pi over 4 to pi over 3. All right, so that's the tangent of pi over 3 minus pi over 3 minus, and then do it again, tangent of pi over 4 minus pi over 4. All right, well, we know our unit circle, so we can use that fact. Let's remind ourselves. Tangent is sine over cosine. So the tangent of pi over 4 would be 1 over the square root of 2 divided by 1 over the square root of 2, which is 1. So this number right here is 1. And then for pi over 3, the tangent of pi over 3 is, again, sine over cosine. So it's the square root of 3 over 2 over a half, which is just the square root of 3. So this is the square root of 3. So our final result is the square root of 3 minus pi over 3 minus 1 plus pi over 4. And the only thing else we can do is we can combine the two pi over 3s and pi over 4s because they're both, well, they both have pi in them. So it's the square root of 3 minus 1 minus, and this is 4 over 12, and that's 3 over 12. So that's pi over 12. And of course, you're welcome to come up with a decimal approximation if you so desire. In fact, I'll do just that in Desmos. This is the original definite integral as it was given. This is after the trig substitution. I did have to cancel the secant. It didn't really, there was a secant in the denominator and numerator. So it's technically like the second step in there, but that's fine. And then here's my final result. And you can see that they're all about 0.47025. So they all work out. The trig substitution changes how the integral looks, but doesn't really change what the integral is. It's still the same problem that you started with. And that problem has an answer of about 0.47025 that we checked with Desmos.